Let's look at an example where we have a device that measures temperature continuously. Okay, so first let's write the topic average value of a function. And these pearls of wisdom are in section 6.5. So imagine a function that measures, or a device that measures temperature continuously over a period of 1 day. Now, if it's an analog device, then it measures all the time. If it's a digital device, it measures either every hour, or every minute, or every second. There are devices that measure that quickly. And of course, we want to come up with a single number that gives you the average temperature for that period of 24 hours. Now, it was easy if you measure every, let's say, couple of hours, then we would have 12 measurements. We add the measurement, divide by 12, come up with the average temperature, right? Even if we measure every hour on the hour, or every hour on no matter what, we'll have 24 measurements, and we sum the temperature and we divide by 24. But what happens if you have continuous, let's say every second or every millisecond? Again, there are devices that can measure that quickly. How are we going to come up with the average value? Well, that becomes a non-trivial question at this point. So if this is T, measured, let's say, in hours, and this is the temperature measured either Celsius or Fahrenheit, and the curve is doing something like that, cold in the morning, at midnight, get cooler a little bit, and then as the day warm up, it goes up and then go down, like so, okay? And then, of course, it's going to get warmer tomorrow. Let's say the cutoff is right here. What will be the average function? Something like this. The value right here, we can say, okay, for this day, this is T bar, and this notation is the average. Okay. So one way to do it is say, okay, you know what? I'm going to go ahead and take samples every delta t. So here's delta t, and I'm going to divide it. So this will be 0, this will be t1, t2, t3, and so on. And the last one will be t sub n, something like that at the end of the day. Okay? And what I'll do, I'll take a measurement somewhere in the middle of each interval. Remember how we did Riemann sum? So if this is delta t, let's say delta t is the difference between t sub 1 and t sub 2, or t sub 2 and t sub 3, then right here we have t sub 1 star, and here we have t sub 2 star, and here we have t sub 3 star, and so on, like we did with the Riemann sum. We took some value. It can be midpoint or any point in between intervals. And we're going to say that the average daily temperature, T bar, right, which is T average, if you want, equals to what? We can say it's going to be approximately equals to the temperature at T star sub 1 plus T star sub 2 plus dot 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 all the way to the last measurement, T sub n. And it's an approximation because there might be some variation in between that we don't take into account. Okay, so of course we'll have a more accurate measurement if we make the delta t, the sub-interval, smaller and smaller, which indeed what is the definition of integration. So using sigma notation, I can say this will be the the sigma is the index, the counter I goes from 1 to n of t sub I star, like so, divided by n, right? And actually, I'm going to take the n outside because n is a fixed value as far as the sigma is concerned, so pull it out, like so. Now, suppose that the time, I'm generalizing, instead of going 0 to 24, let's say we measure 24 hours from t equals a to t equals b. So this will allow me to generalize it to any function. Okay? So what is delta t? Well, delta t, if you think the time interval, again, going back to our calculus 1 treatment of area underneath a curve, it will be the difference between b and a divided by n. N will be the number of sub-intervals. How many divisions we have. Since we have 1 over n, I can see that n by itself equals b over a divided by delta t, and 1 over n, which I need, will be delta t divided by b minus a. Okay? I'm going back to the approximation of the average temperature now. And I said that this is the approximation was the sigma of 1 over n, but instead of 1 over n, I have delta t divided by b minus a, like so. And then I multiply it by the sum, sigma from 1 to n of t sub I star, t star sub I, like so. Again, delta t, since delta t does not depend on the summation from n1 to n, it's outside, but for a reason that will be clear in a moment, I'm going to put it inside the summation. So I'm going to rewrite this summation as 1 over b minus a sigma I goes from 1 to n of t star sub I multiplied by delta t. Can you see why I did it? Can somebody tell me what will be the next step? Detect the limit. This is Riemann sum. We want to remove this approximation. So we'll have exact value if we let n go to infinity, right? We'll have infinitely many divisions such that delta t will be very close to 0, and we'll take the limit of Riemann sum, but by definition, the limit of Riemann sum is the definite integral, right? So, and that will be the next step. So, here it comes. So, again, t, right now we have the approximation. Again, I'll rewrite the last expression. And now, if we let n approaches infinity, now we have t becomes, instead of approximation, we have an exact value, will be 1 over b minus a, because this is a constant, has nothing to do with the limit. The limit as n approaches infinity of sigma I goes from 1 to n of t star sub I delta t. Now, this is the definition of the definite integral. So we end up having it's equal to 1 over b minus a, the integral, the boundaries are a and b of f of t dt. Okay? And if we want to generalize it, so if you want to generalize then f bar equals 1 over b minus a integral from a to b of f of x dx. And if you want to write it as a theorem, and what we did really is we just proved the theorem. Okay? So in terms of theorem, we can write the following. Suppose f is continuous on the closed interval a to b. Then the average value of f is given by, and here we write f bar, the average value will be 1 over b minus a, the integral from a to b of f of x dx. Okay, this is the average value of x, of f, and the next I'll give you an example, and then I'll give you another little theorem. So here's a quick example here. In this example, we're going to let f of x equals 1 plus x squared, okay, and it's defined on the closed interval -1 to 2, and what we need to do is find the average value, f bar. This is pretty much one line solution, okay, f bar, the average value will be 1 over b is 2 and 1 and a is -1, so 2 minus -1, the integral from -1 to 2 of 1 plus x squared dx, and so it will be 1/3 the antiderivative is x plus x cubed over 3 evaluated from -1 to 2, and if you do it, you come up with 2. Okay. So this is a quick example.